In an earlier video, we defined the derivatives of the inverse trig functions. So let us take a look at where that comes from. The derivative of arcsine x is 1 over the root of 1 minus x squared, and the derivative of arccos x is minus 1 over the root of 1 minus x squared. Now, to get to that derivative, you must be familiar with implicit differentiation and also the property that sine squared theta plus cos squared theta is equal to 1. So let's start with sine. Now, if you remember how we defined arcsin, we had to limit the domain because we wanted a one-to-one function of the sine function. So x is between minus 1 and 1, and then y is between minus pi over 2 and pi over 2. Now, we actually defined the inverse function on the closed interval, but the derivative, we're only going to look at the open interval because we don't want to look at the derivative at the point where that function ends. So we're looking at the open interval. So what have we got? We're going to start by saying let y be equal to arcsine of x. So if that is equal to y, what we want to do is we're not going to use the definition of the derivative. We're going to use implicit differentiation. So if y is equal to arcsine of x, then sine of y is equal to x. That's how the inverse function is defined. And now I'm going to use implicit differentiation. So on the left-hand side, I've got sine of a function of x, and the derivative of that is cos of the function of x times the derivative of the function. On the right-hand side, I've got x, and the derivative of that is 1. Now, since y is between minus pi over 2 and pi over 2, I know cos of y is non-zero. I'm going to sketch cos of y between those two. Cos of y is going like this. That's pi over 2, and that's minus pi over 2. So I know cos of y is definitely positive. So I can divide by that. So dy dx is 1 over cos of y. Now, in the property up here, if I make cos the subject, then generally I know cos of y is equal to plus or minus the square root of 1 minus sine squared y. But in this interval, I can see that cos of y, I wrote greater than 0 up here. Cos of y is non-zero. That's the first thing we look at. But we can also see it's positive. So I can rewrite that as 1 over the square root of 1 minus sine squared y. And I don't have to have plus or minus the square root because we know cos of y is positive there. So that's good. And that I can rewrite as 1 over the root of 1 minus x squared because x was sine of y. And that is the derivative of arcsine x. So similarly, let's look at the derivative of arccos. It's minus 1 over the root of 1 minus x squared. X is between minus 1 and 1. Now in this case, y was between 0 and pi in that interval. That's where I had to chop it off so it can be 1 to 1 so we can define the inverse function. Now it's very strategic. It works for the derivative very nicely. If I say let y be equal to arccos of x, then I know cos of y is going to be x. Implicit differentiation again. On the left-hand side, the derivative of cos of a function is minus sine of the function times the derivative of the function. The right-hand side, the derivative of x is just 1. Now, let's look at sine on this interval between 0 and pi. Well, this is pi. So between 0 and pi, I see that sine of y is positive. And when it's positive, it's obviously non-zero. So I can divide by sine of y. So dy dx is equal to minus 1 over sine y. And similarly, as in the previous one, make sine the subject of that formula. So that is minus 1 over the root of 1 minus cos squared y. Now, we don't have to have plus or minus the root because we've already established that sine of y is positive. So you've got to make note of that you did take that into consideration. And that's minus 1 over the root of 1 minus x squared. And there we go to show that the derivative of arcsine and arccos is what it is. Now you can use a similar technique for tan. It will work the same way. So that is all the proofs for why the derivatives are what they are.